In this video, we will take a look at how to use the Keras framework in order to do machine learning with neural networks on a simple example based on the famous iris dataset. This is sort of a standard benchmark dataset which is used in a lot of different applications. It's available through the Keras framework and actually through the sklearn packages of datasets. So it's easily accessible. Therefore, we will use this. The code is based on the book Hands-on Machine Learning with Scikit-learn, Keras, and TensorFlow. And the code which I am basing this example on is found on page 297. So I will just do this sort of live coded. And you can try and follow along to see if you can make your setup do the same. So the first thing we need to do is import Keras framework. I have already all these things installed. If you don't have them, then you need to do that first using pip, for example. Then we need to load our dataset. So we're going to do that by loading this load iris. I will just add a function here, which will be used to implement the actual application. And then we just call that from our main method here. First thing we want to do is load data. And we also need to slice the data into separate parts. So we need to pick out what is the input vectors that we're going to use. Loading the data is very easy. We just use this load iris function that we just now imported. If we set a breakpoint here, we can take a look at what this looks like. So we see here that the iris method here is going to give us a bunch data package, which has one property called data, which is a NumPy array. And there is also a property called target, which is also a NumPy array. So in this case, the data, that would be our input data, and the target is our output y. So data is the input x, and target is the output y, in reference to the nomenclature I used in the neural network and machine learning videos. So from here, we then just construct our inputs. So let's say that x, we want this iris data property. And we're going to take a slice of that, say that we want all the rows, and we want columns number 2 and 3, like so. And this is the petal length and petal width. So the iris data set is a set of manual measurements taken of the petals of iris flowers, together with a representation of 3 different types of iris flowers. It's a very famous data set, so if you are interested in knowing more about the details, then Google is your friend. You will find a lot of examples of this iris dataset. Next, we are going to limit ourselves to look at only 2 types of iris flowers. So we want to see just one of those 3. There's 3 types of iris flowers in the dataset, and we are going to just try to model how to detect one of them. So we say that we want y to be whatever this target array contains 0, and then we want this to be cast into an integer, which we do like so. Actually, let me use a float here. It's not a big deal. Yes. So before we continue, it's always useful when we do any form of machine learning to have an inspection of the data, to sort of look what we are actually working on here. So I want to make a plotting function which will just make a plot of the data that I'm now going to apply neural networks to. And then I want to do a scatter plot. So let me just import here matplotlib. This one. Then we do a scatter plot like this, where we say that we want x versus y. Now we know that in y there's going to be zeros and ones, and in order to separate which of the x's are, or which of these data points are, sorry, this is wrong, we don't want to do that. We want to plot x now has two columns, the petal length and the petal width. So we want to plot the first column, which is going to be petal length, against the second column, which is going to be petal width. And then we're going to do just a plot show on that. And then let me just run this to see what that looks like. So we see here that this is going to be our data points. We have one group here and one group here. But now they are both blue, which is not very useful. So to try to get a better image, we're going to extract first the indices of the data points which has a reference value of 0. And similarly, we want to see the indices wherever y is equal to 1. So we know that y is going to be 0 or 1, because we imported it like that here. It's going to be just binary values converted to floats. Yeah, I see I need to import NumPy here, like so. And now we will just, instead of plotting all the rows, we will plot y0, and then we set the color here equal to red. Just make a copy of this, and then we plot the indices in I1 in blue. So what's going to happen now is that the data points in X, which should be predicted as y value 0, they will be red, and the ones where we have y value 1, they will be blue. So we run this again. So this is going to be our y0s, sorry, y1s, and this is y0s. Yes. This is the zeros, this is the ones. So now that we have our data, we're just going to comment out the plotting because we don't want to see that every time we run. We will have to set up a simple neural network model. So the first thing we're going to do is import this perceptron, which is the most simple neural network with a sign operator activation function, which we can simply from Keras import by writing this. Sorry, I need to import that also. That should be here. So we're going to do from scikit-learn linear model import percept, like so. Like this. So that constructs our model as a perceptron. It's just a very simple perceptron one neuron network, which is just a sign operator over the weighted sum. And then we're going to fit that model to the data we have, which we just do by calling the fit method, like so. And then we say fit x to y. And then that's basically what we're gonna do in the first test here. So let me just run this to see what happens. So now if we inspect the model object here, you see that this is a perceptron. It has been fitted. We see that we have two features in, which is this X here has two columns. There's no penalty function, which means there's no regularization. So this is the simplest possible neural network we could ever do. It's just one neuron with the sign activation function. You can actually here also see the coefficients. So this is the weighting parameters, which is -2 for the first coefficient and -0.7 for the second coefficient. That's the result of training this perceptron on this dataset. That's the weights that we find as optimal. So now that we have fitted a neural network, as you can see, it's basically, for this simple case, it's just 2 lines of code to the dataset. We can now try to do some predictions with it. So let's just generate some test data. So I'm going to just generate a new dataset, which we will do as follows. So this is just some data points that I constructed, which I know from experience is reasonable. So we expect these 2 data points here to be of type 1 and these 2 data points here to be of type 0. And just to sort of convince ourselves that this is correct, let's extend the plotting method here to also plot our test data. So then we're going to just do this. Here we will plot all the rows. Like so. Let's plot those in green, for example. So yes, then we'll run that. Yeah, of course. Like so. So here we have 2 data points down here, which should clearly belong to the blue group, which was the 1 output, and 2 data points over here, which belongs to the 0 group, like so. And we can just verify that the model indeed predicts those correctly by calling up the predict function on our model. And then we say test data, and we call those y predicted, and then we just print this guys here. I should comment out plotting so we don't have to look at that every time. And indeed, y predicted turns out to be exactly what we expected. The first 2 data points here belong to the 1 group, and these 2 belong to the 0 group, which is the upper right, the blue ones. So that's basically the example from the book, which I was following along. We see that this perceptron is very simple to get to work. It's basically just 1 neuron with a sign operator, so it's hardly a network at all. But just because we can, let's try to do this in a little bit more interesting way, something which is more, what shall we say, useful. So the Keras framework also supports this sequential API framework, which can be used to build layered network structures sequentially. I'll show what that means. So now we want another model, which we are going to import from Keras models, and we're going to import the sequential model type like so. And the way we use the sequential model is that we can add layers to it. So now I want to build a feed-forward network. Which I will do using this method here. Seem to be missing an import here somewhere. Let me just add some imports from Keras like so. So like this. I will of course make the code available together with the video if you want to follow my coding a bit more closely. So the first thing I want to test is a feed forward layer with just say one neuron, and then I want the activation function to be a type, let's see, activations. Let's use just a hyperbolic tangents activation function like so. So in the sequential API, this is how we would construct a feed-forward neural network with one layer with exactly one neuron. And the feed-forward types is called dense, like so. But we're not quite done yet. This basically configures the structure, and this is actually now running in TensorFlow behind the Python code. So what this sequential API really does is configure the TensorFlow framework to run the structure that we configure in this way. And therefore we also have to call a compile step in order to complete this configuration of TensorFlow. So it should be model 2, obviously. So we're going to call the compile function, and here I'll specify first which loss or error function I want, which is going to be the Keras losses and then the mean squared error. You can of course here experiment with different things. Then there is an optimizer. We have to choose which optimization algorithm to use. If you want to know more about what these different things are, then look at the video which gives an overview of neural networks and deep learning, which will go into some details on what these different things are. And finally, we will just add an output metric here, which is going to be the accuracy. Like so. So if we run this now, what we are going to end up with is a model configured in the background for TensorFlow, which is sort of ready to be fitted to data. So the last thing we'll do now is just fit the model to our data in exactly the same way as we did before. Let me just break there. We get some error messages there, which is because I'm missing some installs on TensorFlow to make it run on GPU. But those are of no consequence to us. So here we have the Keras engine sequential object. We have definitions of the input, which is this two-dimensional shape, because we have two columns in the X here. This is specifications of everything that we have configured. But of course this is now just a trained model. What we are really interested in is to see if this model is able to predict our test data. So we're going to call again this ypred2 like so, and then we do a print of that one. We're just going to turn off here the output that it generates while fitting, and then we're going to run this again. So now something very interesting happened. So here we have the perceptron results, which is very nice, 1100. It's exactly what we expected. But this one here is completely wrong. This is not at all what the output should be. And this is very typical of any application where we do neural network training, that we see something, the first results, what we're trying to do, almost never works. And the reason is that we need to do hyperparameter tuning. So now I have made several decisions, which is just more or less random guesses. For example, how many layers do I need? What width of layers do we need? Which activation functions to use? What loss functions to use? What optimizer to use? And so on. And all of these things is now basically just random guesses. I have no basis on which to say what those parameters really should be. And the only way to find out is by trial and error. So the first thing I will do is add an argument to the fit function here, which is the number of epochs, that is the number of iterations I want to train. In the default, this is set to something very low. That's going to be the first thing that I test, to run the training for a few more epochs. Should be an S there. So now we are running for 100 epochs and we still don't get anything very interesting. So let's try to run the training a little bit longer. Still not really doing anything interesting. We get 1111 pretty much. It's also not very interesting. We can do 4000. Now we start to see at least something happening here. We see that the first two predicted Ys are relatively high, and the last two is relatively low. And as we remember from before, we expect these two to be 1 and these two to be 0. That would be the ideal case. But still, this simple little neuron here is not able to give us very good prediction results. So one thing which we can do is make a modification to our reference data. For the perceptron, it's pretty okay to just have zeros and ones, but in general, for neural networks, it's better to have some sort of balanced output. So we could do a simple modification like this, which will then change our zeros to a -1 and our ones to a +1. If you take a minute to look at this simple function, you will see that 1 minus 0.5 is 0.5 times 2 is 1, and 0 minus 0.5 is minus 0.5 times 2 is -1. And actually for neural networks, it's better if we don't use the reference values 1, but instead, let's say 0.9. This is because those activation functions that we use, they sort of saturate at 1. So if we train to be in the area where the function isn't fully saturated yet, by experience, that turns out to be more, it turns out to give better results when we do neural network training. So this is now kind of an example of something called one-hot encoding, where we have a class output, which is going to be around 0.9 for one of the classes and minus 0.9 for the other classes. You can try and run this again and see if that helped. Yeah, so we see right away we have much better results. We see that the first outputs is close to 0.9, which is what we expect, and the two second outputs is close to minus 0.9, which is also what we expect. But we can do one further experiment here, which is to maybe adjust the structure. So let's say that we allow 3 neurons in the first layer, but then we have to add a second layer to collect the output of those 3 first neurons into our single output, because the output Y is just one column, so we can't have 3 neurons which will then give 3 outputs. That wouldn't work. Instead, we want them to have one layer, one output layer, which has always one output neuron, because that's what we have in the data. So now we can run that again. Of course, we are running 4,000 epochs, so it takes a while. You see now, this is a pretty good result. We have 0.9 here and minus 0.9 here. So that's what we expect. This would then be equivalent to ones. So 0.9 is equivalent to a 1 from the perceptron, and minus 0.9 is equivalent to a 0 from the perceptron. And with a little bit better structure, maybe we can reduce the network complexity, because it is now easier to fit the data. Well, yes, we see with 1,000 epochs, it's still not too bad. One last thing which I want to show is that if we now run this repeatedly, observe that we now get different answers every time. And I mentioned this in one of the videos on neural networks, that when we build a neural network, the initial weights, the starting point of our fitting or our optimization of neural network training weights, is randomized. And that means that every time we run this training algorithm, we will get different results. And that is to be expected. That's just an effect of having random initialization of the training weights of our neural network. So that's it. I'll upload the code together with the video, and I encourage you to also do some more experimentations here, different structures, different activation functions, and see what combinations work and what doesn't work. And then I will follow up this in a later video, also to show how we can use Keras to set up a sequential API for a time series based neural network. It's going to be an AR neural network.